I was watching Joe's classic video games channel where he was walking through a repair of a Space Invaders machine a little while back, and I thought it'd be fun to build some of the analog sound effects from that game, and in the process learn some things about kind of older style analog sound effects. The schematics for Space Invaders, both the Midway and Taito versions, are available in quite a few places. I'll include a link below where I sourced mine. What you're looking at here is the Taito version. I'm going to be walking through a few of the sub-circuits in this video, and hopefully I'll do a part two where I'll walk through some of the more complex versions. But the three sub-circuits we're going to walk through in this video are this one up here, which is a noise generator. And then we'll move on to the famous Space Invaders step sound, which is this circuit right here. And then finally we'll look at this circuit here, which is called mysteriously flash here, but it's actually the sound when the player gets killed. As usual, I've included a list of sources for the various components that I've used in these circuits here. And as always, I've got no affiliation with any of these vendors. It's just where I was able to find the components that seem to work. Let's just move on. Before going any further, a little note on this LM3900 OpAmp that kind of is quite ubiquitous in the Space Invaders circuitry. And when I first tried to do some simulations in ltspice of these circuits, I was getting crazy results. But what I soon discovered is the LM3900 is a Norton OpAmp rather than a sort of a traditional OpAmp. And the basic difference is a Norton OpAmp works by amplifying the difference between the current of the inverting input and the non-inverting input rather than the voltage of a traditional OpAmp. Now, the Norton OpAmp itself is a whole subject in itself, and one that I feel is a little beyond me. But I will leave a link to an excellent TI applications document where they describe a whole pile of different circuits, how you do the calculations for the input current, and how do you actually create, for example, a simple non-inverting amplifier, and so on and so forth. Now, I was able to source on the ltspice discussion group a model for the LM3900, and I do have some ltspice models here which reasonably faithfully capture what's going on in the circuit. One thing to note is the Norton OpAmp does have a different symbol, and let me just bring up kicad here and show you that. So here's a Norton OpAmp, bear with me, I've just got to get it. So here's a Norton OpAmp right here, and you can see the Norton OpAmp has this little downward pointing arrow with a circle in it, so that tells you that it's a Norton OpAmp. Now, interestingly, the original schematics don't have that, so whether this was a symbol that was introduced after those schematics or not, I don't know. But anyway, so let's move on now to the first example, which is the famous Space Invaders step sound. It's actually funny, as I was looking at this symbol, I've realized I've got the non-inverting input and the inverting input around the wrong way. So the little arrow points between the inverting input and the non-inverting input. So I just should have this plus and minus swapped around. I'll get that fixed and come right back. Okay, so there's the symbol correctly rendered. The little arrow here goes between the inverting input and the non-inverting input. So anyway, that's corrected. So let's move on now to the stepping sound. Okay, so here's the circuit at the top here for the stepping sound that I've rendered in kicad. Now this cluster of FETs over on the left-hand side replaces the original hex buffer drivers in the original circuit. And obviously I wasn't going to sort of go the whole hog and drive this from an 8080 CPU like the original. So what I'm doing is driving it from an ESP32, and I'm using that just purely for switching duties. And so effectively what I'm doing here is that 5 volts will be passed through to here if this FET is turned off. So basically, in order to enable a specific stepping sound, I turn the specific FET off. That has 5 volts passing through whichever portion that I'm turning off here, and that goes to the 556. So let's cover the stepping circuitry in a little more detail. Now, this uses a 556 timer, which is effectively a 555 timer in a dual package. So you've got 2 timers in the single package. You can certainly use a 555 timer if you have them handy, but I thought I'd stick to the original circuitry here. And the different tones are caused by having the 5 volts applied to different resistance values that go through to the discharge pin on the timer itself. So the lower the resistance, the higher the tone that's emitted. After the timer, so anyway, basically what will happen here is that the timer will emit from its output pin here what's effectively a square wave. Now these square waves are from around about 50 hertz for the lowest tone all the way up to around about 70 hertz for the highest tone. And then subsequently that square wave is passed through this low pass filter here to accentuate the low frequencies. And then finally, the output of each of these circuits actually uses the same output. And again, this isn't original. There's a whole amplifier sectional in the original Space Invaders machine. You'll see that on the schematic, and it consists of some more LM3900s together with some LM377s. But I've just got a simple circuit here where I've got an LM358 as a buffer, and then running through the classic LM386 through to a speaker. So here's the circuitry on the breadboard. So obviously there's the ESP32 off to the left-hand side here. Here's that cluster of FETs, which is used to switch in the various resistor combinations for the steps. Here's the resistor combinations right here, and together with a diode, and the diode is there to, obviously when each one of these switches is turned on, it's going to be grounded, so the diode makes sure that the 556 doesn't see that ground. And then over here we have the 556 itself, so the output of this resistor bank goes to the discharge pin on the 556 right here. And then the output, that square wave on the output of the 556, goes through to the low pass filter, which is over here, and then finally through to the LM358 buffer, and then off down here to the LM386. So anyway, let's hear that. Let's hear that in action. So I'm just going to plug the circuit in. And you can see that's a reasonably faithful rendition of the Space Invaders stepping theme. Now, obviously, the ESP32 is controlling the timing there, and that would be the 8080 in the original. But anyway, that's the stepping sound. I thought what might be interesting is to have a look at the stepping sound on the oscilloscope and just have a look at the waveform that's emitted, and then we can move on to the next example. Okay, so here's the waveform on the oscilloscope, and let me just pause that. Turn down the... let me just turn that down so you can see that. So there's the waveform there. As you can see, after it passes through the low pass filter, it is no longer a square wave. But there you can see the output there, and each one of these steps obviously is a slightly different frequency, and you can see that in the output there. So anyway, that's the stepping sound. Let's move on now to the noise generator. Okay, let's move now to the noise generator. The noise generator's job is to produce a pseudo-random stream of constant amplitude pulses, which are used by the game to simulate explosion sounds and so on and so forth. The random stream itself is produced by this CD 4006 18-stage static shift register, where feedback is taken from two or more of the outputs here, run through an XOR gate, and then fed back into the input. There's a great article on EE Times, which I'll provide a link to, that explains kind of how this all works. And the trick is choosing which taps of the output to feed back into the input to produce a maximal length, random length, pseudo-random length of bits output. Now the frequency of the pulses is set by this clock here, which comes from this XOR gate oscillator right here. It's an interesting little oscillator circuit here, and basically what happens is this is held high, this is held low, and then to start with, this basically is high, which charges up this capacitor through this path here and then through to ground. As the voltage right here rises, ultimately it turns on this XOR gate here, and then when that happens, the cycle reverses. So this becomes high, and a high with an XOR gate produces a low, and then this capacitor then discharges through this resistor here to the ground here, and then the cycle repeats. Now basically what this XOR gate combo provides is around about an 8 kilohertz signal. So let's, enough talk, let's have a look at this on the oscilloscope, and we can see the this point here and this point here. Okay, so here's the two ICs here. Here's the quad XOR gate package on the left, and then we have the shift register on the right hand side here. So to have a look, first I'm probing the pin 11 on the XOR gate, and we should see that nice square wave coming out of the XOR oscillator. Okay, so here's the output from that XOR pair oscillator, and you can see it's around about 8 kilohertz output signal. We've got a nice clean square wave there. So let's now look at the output of the shift register. So basically that oscillator is acting as the clock input, and then through the feedback network where the output goes back in through that XOR gate to the input again, we should see that pseudo-random stream of bits. So let's have a look at that now. Okay, so now I'm probing pin 10 on the shift register here. And let's move up and have a look at that, the output on the oscilloscope. Bear with me while I just transfer this over. And you can see there's that, let me just pause that so you can see it in a bit more detail. Oops. So there's that output, and as you can see, it's a nice, let me just run it a little bit. And as you can see, it's a nice pseudo-random stream of bits. And like I said, this effectively generates a white noise, which is then used by all the kind of the other circuits to do with explosions and missiles firing and so on to kind of produce that explosion effect. So let's hear that pseudo-random stream on the speaker and confirm we are getting some white noise out there. Okay, so I've connected the output in the noise generator pin 10 to the input of the buffer LM358. And so now let me just turn this up gingerly because it does get loud, so just headphone users beware, this does get a little loud, but let me just turn it up. So yeah, there you can hear the, turn it down so I can speak. So there you can hear the white noise output from that circuit. And I think it's quite an effective little circuit. I mean, obviously noise generation is a whole subject in itself, but that's a kind of a little simple circuit to produce some noise here. So let's move on now to one of the sub-circuits that actually uses that noise as its input, and that's the player-killed explosion sound. So now we move on to the player killed sound and the first use of the LM3900s. So here's the circuit here, and let's break it down into its constituent components. So the first section over on the left hand side takes a momentary voltage impulse through here. That's applied by effectively grounding this 12 volt line here. And it turns it into a voltage input at the output here with a specific duration, and that duration is controlled by, amongst a few things, this 2.2 microfarad capacitor right here. So let's have a look at that impulse on the oscilloscope, and we'll start with the 2.2 microfarad cap, and then we'll replace that with a 470 nanofarad cap, and what you should see is the impulse duration decreases.
Okay, so my apologies for seeing this. It's a bit hard to see, I know, but I've got the oscilloscope probing at the output of that first LM3900. Let's move up to the oscilloscope, and we should see that trace where it sustains the output with a momentary input. I'll just click on the button. And you can see there's that sustained output. So I'm just doing a momentary click, but that 2.2 microfarad capacitor is interacting with the LM3900 to produce a sustained output. So let me now swap that 2.2 microfarad capacitor with a 470 nanofarad capacitor, and we should see a pulse that is of lesser duration. So I've swapped out the 2.2 microfarad. Now we have a 470 nanofarad capacitor in there. I'll do the momentary impulse again, and you can see that the duration of the trace is significantly less. So let me just so we're on 100 milliseconds per division there. So you can see we've got about 150 milliseconds of pulse there instead of it looked like about half a second of duration on the pulse. So that's how the sustain of the pulse is controlled. Let's move on now to the attack and the decay, and that's controlled by a combination of the capacitor on the output, that 1 microfarad capacitor on the output. So let's just move back to the circuit and see that quickly.
Okay, so here we are back on the circuit. So now the attack and decay of the envelope is controlled in two ways. So the attack is controlled with this combination of the 10K resistor together with this 1 microfarad capacitor. And then the decay is controlled by this 1 microfarad capacitor in combination with this 680K resistor as input to the second stage here. So we'll do the same thing again. We'll have a look at that envelope. I'll be probing right here on in the output, and we should see that a nice attack and decay slope, and then we'll adjust some of the values of some of the components, and we'll see what we see. All right, let's move back to the oscilloscope.
So I'm probing just on top of that 1 microfarad capacitor. And let's do the momentary pulse again. And I've put the 2.2 microfarad capacitor back in there, so we should see the longer sustained time. So as I press the button, you can see there's that nice, let's actually increase the time base a little bit so we can see that a bit better. So there's the attack and decay right there. Let me stop that so we can sorry about that. Let me stop that. There we go. So you can see there's that nice attack and decay there. Let's just move over a little bit so we can see. There's the attack. The sustain duration is controlled by that 2.2 microfarad capacitor, but the attack is controlled by the 1 microfarad capacitor in combo with the 10K resistor. And then the decay is controlled by the 1 microfarad capacitor in combination with the 680K output resistor, which goes to the following stage. So let's see the effect of what I'll do is I'll change that 10K resistor to let's say a 47K resistor, and we should see the slope of this attack reduce. So anyway, let me get on and do that, and then we'll redo. Okay, so I've got a 47K resistor in place of that earlier 10K resistor. Let's do the momentary pulse again. And you can see there, let me just stop that. Oh, I wasn't quick enough. Let me do it again. So you can see there the attack is significantly flattened out. If you recall before, it was quite a rapid rise. So now, unfortunately, it's difficult to control the on the output side because the 680K resistor has to be balanced with the 680K resistance on the output side. But what I'll do is I'll change that 1 microfarad capacitor to a 470 nanofarad capacitor, and you should see the decay will be a lot more abrupt. So let me get on and do that, and then we can move on. Okay, so I've replaced that 1 microfarad cap with a 470 nanofarad cap. And there you can see the decay now is a lot sharper. So you can see by controlling the values of the various input and output resistors and the capacitors themselves, you've got a really nice full control over the envelope of the output. So let's move on now to the second part of the circuit where that envelope that we've just created here gets combined with the noise output that's generated earlier. Okay, so let's move on to the second part of the circuit, and as you can see here, here's that envelope down here. This is where this gets injected into the LM3900. And then on the other side, on the non-inverting input, we have the noise input coming in here. Now, the way this particular circuit is configured is effectively the signal, the envelope here gets modulated by this, or rather the other way around. The noise here gets modulated by the envelope. So effectively what you have on the output here is that envelope we just saw, but with a noise input. So anyway, that's enough talk. Let's have a look at this on the oscilloscope, and you can see what I mean. So I've put all the components back to their original values, that 10K resistor, the 1 microfarad capacitor, and then let's fire it off. And you can see there's that envelope, but now it's the envelope is now modulated with that noise signal that we've got there. So you can see there's the pseudorandom noise, and the pseudorandom noise is what's going into the envelope there. Now let's, for yucks and giggles, let's probe after the output of that low-pass filter, and we should see yet a different trace. Bear with me. So let's run this again. Fire that off, and there's the output after that low-pass filter. And you can see that's it's quite a different output, but it's got a lot of the higher frequency, the harmonics that's coming from that square wave. They're all removed, and now we have this trace here. So let's, obviously the proof is in the pudding. Let's turn the volume up and let's hear this, what this explosion sounds like. Let's turn it up a bit. Headphone users beware. This does get a bit loud. So there's that explosion sound. That is the, I mean, that's obviously the audio of that trace that we're looking at there. So that's all I had planned to do in this part. I definitely want to move on to some of the more complicated circuits in a follow-up. I've been having a lot of fun with this, and the interesting thing is this sort of stuff is almost trivial in DSP with modern processing techniques, but there's a lot of art, I guess, to the analog designs. I'm having a lot of fun with it. Hope you enjoyed this video. That's all for now. I will be doing a part 2, and we'll wrap it from here.